Welcome to ColeSoft's cXDC class. My name is Dave Cole. I am President of ColeSoft Marketing and Chief Architect for cXDC. In this segment, we will discuss various techniques for starting a debugging session. This class will be guided by this presentation, but when conducted by a live instructor, he will be adding his own insights throughout. Let's get started. Briefly, there are 4 or more ways to start a debugging session. One is in a batch job or system task using the XDCCALL utility. Another is in TSO via the cXDC Startup panel. A third is via a static hook that you compile into your code. And finally, you can start a token cXDC session and use its hook command to start a cXDC session in any other currently running batch job, system security permitting, of course. One of cXDC's very powerful features is the ability to interactively debug user programs running in the batch. There are several ways to start such a debugging session. One way is to start your program under the control of our XDCCALL utility. You will need to make some minor changes to the exec card. First, change the name of the program from whatever it was to XDCCALL. Use XDCCALL A if what you want to debug needs to run authorized. Then insert your target program name into the start of your parm field. Follow it with a blank. That name will be stripped out by the time your program sees it. Any DD cards that your program needs do not have to be changed. Just make sure that they are there as needed. cXDC just ignores them. But depending upon the needs of your debugging session, you may or may not need to add additional DD cards for cXDC to use or simply to see. One common addition is a //tasklib that cXDC will set up to function like a steplib, but in front of your steplib. When your programs are loaded into memory, cXDC sets it up so that the system will check this task library before looking into steplib or joblib or system libraries. Another DD card that cXDC uses is //xdcprof. cXDC has support for saving and reloading a very large set of session characteristics, collectively referred to as session profiles. In order to activate this feature, an xdcprof DD card needs to be present pointing to a fixed block 80 library. This might be the same library as your TSO Sessions ISPprof library, or not. It's up to you. If you prefer, you could use an ISPprof DD name instead. It doesn't matter. When this DD name is absent, the ability to save and reload profiles is disabled. Here are a couple more DD cards you'll need if your program will be running non-authorized, but your load modules are marked either reentrant or refreshable. Normally when a module is marked as reentrant or refreshable, the system loads it into key 0 storage. But then in a non-authorized debugging session, cXDC would be unable to set breakpoints or perform execution stepping. But when these 2 DD cards are present, cXDC notifies the system that such modules need to be loaded into key 8 storage, regardless of how they are marked. This then allows cXDC to set the traps that you tell it to. These DD dummy cards are what we call keyword dummies. cXDC considers the presence or absence of these as parameters. They are never actually opened. They only control certain actions simply by the presence or absence of their DD names. Briefly, the debugging session has the following characteristics. First, XDCCALL's presence is transparent to most programs. XDCCALL supports debugging both authorized and non-authorized programs. XDCCALL automatically sets up the debugging environment. cXDC first receives control just prior to executing the first C statement. cXDC sends displays to your terminal via its server XDC address space. A user connects to the debugging session simply by using option 3 of the cXDC startup panel in ISPF. There are pros and cons to this method. The main pro is that your debugging session can be conducted without source code changes. There are a couple of cons. One is you'll have to make minor changes to your execJCL card, and you also may have to add certain DD cards. The other is your program does not run as a job step task, but very few programs care about this, so mostly it's a non-issue. Pretty much anything you can run in the batch can also be run in TSO. That's because TSO address spaces and batch address spaces are nearly identical in structure and management and capability. So to debug your batch program in TSO, all you need to do is navigate to cXDC's startup panel in ISPF, fill it in, and then select option 2. Simple, right? Alright, let's talk about filling in the panel. Despite how it looks, it's actually pretty easy. The fields of greatest interest are the program name field, the parm field, the TaskLab dataset names, and the field for dealing with reentrant and refreshable load modules. For authorized debugging, this field should be no, but for non-authorized problem state debugging, this field should be yes. So what about the rest of these fields? Well, here's the briefest of rundowns. If you have any questions, please feel free to ask the instructor. First, will your program be running authorized or non-authorized? Usually, you would just say no here. For auto-stepping, say yes. This is what allows cXDC to skip over module prologue code and pause execution at your program's first language statement. If you want cXDC to automatically run a command script at the start of your session, this field is your friend. Normally, though, just leave it blank. If you want to pass lowercase text in your parm field, you can say no here. Most often, though, you will probably just say yes. If you already know that your program has an abend in it, and you just want cXDC to skip its initial display and let executions proceed until the abend occurs, then say yes here. Usually, though, you'll just say no. The TaskLab DSName fields can accommodate a concatenation of up to 6 libraries. Hopefully that's enough. Or you can pre-allocate your task libraries and then provide its DD name here. The ISPF fields rarely matter. Just say no. And you can leave the Apple ID field blank. The Connect to CDF field only matters when you're connecting to a batch job debugging session. But nonetheless, it cannot be blank. Yes is recommended here. And cXDC's name, of course, is guess what? XDC? Finally, put a 2 in the option field to start your debugging session. Option 1 you will probably never use, and option 3 is for connecting to a debugging session running in the batch. So let's summarize. Usually you start a debugging session in TSO by using cXDC's startup panel in ISPF. Pretty much anything you can run and debug in the batch can also be debugged in TSO. Under the covers, the panel runs your program in the TSO address space under the XDCCALL utility. As usual, you can debug either authorized or non-authorized programs. cXDC sends its displays to you via either ISPF display services or TSO full-screen tputs. The pros and cons are these. The cXDC startup panel is pretty easy to use. And as just mentioned, pretty much anything that can be debugged in the batch can also be debugged within TSO. For cons, the user needs to be comfortable with TSO and ISPF. All dataset allocations need to be done ahead of time using TSO's allocate commands. You may want to write a CList or rexexec to do this. Another way to start a debugging session is to modify your program to call the XDCHook function. Simply include the header file into your program, and then call the function at the point in your program that you want to start your session. We distribute the cxdchook header file in the dbccall.xdcz22.xdcsamp library. The header file maps the cxdchook function to either of two assembler programs, aXDCHook for 31-bit C or aXDCHOK6 for 64-bit C. Those programs are located in the dbcall.xdcz22.xdclink library. cxdchook takes one argument, a 3-character string giving cxdc's name. Normally that will just be XDC, but it could be different, Z23 for example, if you've also installed a beta for cxdc's next release. So yeah, cxdc can have different names, and that's where cxdcis comes in. It allows your program to react to cxdc's current name at execution time, so you don't have to hard-code its name at compile time. cxdcis is a function that checks the current file allocations for a DD name of the form XDCIS and a 3-character name. So if your cxdc is currently named Z23, for example, then you would include a DD card or allocation for XDCIS-Z23. But if you're using a cxdc with its normal name, then you could either create an allocation for XDC is XDC, or you could leave the allocation out entirely. cxdcis returns to its caller either with the allocation's 3-character name value or with XDC if the allocation is not present. Like cxdchook, the cxdcis header file can be found in dbcall.xdcz22.xdcsamp. When you start your debugging session with a static hook, you can just use your program's normal JCL without changes. However, if you want to be able to load and save session profiles, then you will need to add an XDCProf DD card for that. ISPProf, XDCProf, it doesn't matter. cxdc accepts either. Normally, ZOS loads reentrant and refreshable load modules into fetchable key0 storage. This makes sense since such modules are supposed to not be self-modifying. This is not an issue when debugging authorized programs. In such environments, cxdc is completely capable of setting its trapping and stepping zaps into key0 code. But when cxdc is non-authorized, it cannot set traps or perform stepping in key0 code. So you'll have to run a special set of scripts to make cxdc itself authorized, so the stepping and trapping can be done. The program you're debugging remains non-authorized. Only cxdc itself becomes authorized. This capability, of course, is protected by security rules. Finally, when set up properly, cxdc does a pretty good job of getting in front of LE's eStays and kneecapping LE's eSpies, so C's trap runtime parameter has no effect. You can leave it off entirely. Of course, for Metal C, LE is not an issue. Here is the JCL used to compile CSAMPLE. You can find a copy of this in our XDC JCL library. The JCL is pretty typical. The sysin file points to where the source code is located. We point the syslin file to our XDC OBJ library, but of course you can put it anywhere you want. We want the compile to produce dwarf data, so we put debug in the parm field, and we've included a sysc debug DD card pointing to our dwarf library. Finally, we need to have an lsearch compile time parameter to tell the compiler where to look for the cxdchook and cxdcis header files. Other than that, the JCL is pretty typical for an XLC compile. Here is the JCL used to link edit CSAMPLE. You can find a copy of this in our XDC JCL library. Pretty normal stuff. There isn't much that's special here. Just notice that the XDC link library has been added to the autocall list. This is where the binder will find the cXDCHook and cxdcis modules. The output module is going to be a program object, so the load library needs to be a PDSE, not a PDS. The rest is pretty much what you need to have when binding C programs. To summarize, the cxdchook function creates static hooks in your program. Static hooks create debugging sessions upon being reached by execution. Static hooks are permanent. They cannot easily be removed until you recompile your source. Both authorized and non-authorized programs can be debugged. When your debugging session starts, cXDC will receive control and display your code starting at the statement following the function call. All registers and other state information are preserved, of course, and displayed upon request. Here are the pros and cons for this method. The main pro is that your debugging session can be conducted without having to make any JCL changes. The main con is you have to change your source code to call the cxdchook function. Perhaps the easiest way to start a debugging session is by using a cross-address space dynamic hook command. This allows you to start a debugging session on the fly in any program in any currently running address space in the system, security permitting, of course. Here's one way how to do that. Start by navigating to ISPF's command shell, also known as =6. Now start an authorized token debugging session against anything. IEFBR14 is an easy choice. Next, use cxdc's setASID command to direct cxdc's attention to the desired address space. Maybe use the map command to load module and source image maps of the target program. In any case, you probably want to use the format command to display the target code. Now use the hook command to set a dynamic hook in the target code. At this point, you can end this token debugging session, or not, but it's done its job for now. Now do whatever it takes to cause execution in the target address space to reach the hook. This will cause cxdc to receive control in the target address space. Now navigate in ISPF over to cxdc's startup panel, and then select option 3 to connect to the debugging session. Often =D.3 works, but that depends upon how the startup panel was installed on your system. For option 3, most of the rest of the panel is ignored. Only the very bottom field matters. Dynamic hooks are very powerful devices. They are created by cxdc's hook command. They can be used to start debugging sessions pretty much anywhere you want. There is even a deferred variety that can target modules yet to be loaded into memory. When a hook is reached by execution, a debugging session is created, and the first display shows the next instruction or statement to be executed. And of course, all registers and state information are preserved. Debugging sessions created by dynamic hooks always get in front of all currently existing eStays. This is a cXDC requirement. Dynamic hooks are always automatically removed upon first execution. The pros and cons of hooks are these. Hooks can be used to create debugging sessions on the fly without having to prepare the target program in any way. The target program may reside anywhere, in any address space, in common storage, or even in future loads into the current address space. Dynamic hooks can be used to overcome interference from eStays newly created between now and a future trap target. For cons, the target address space must already exist. If the target job is not yet running, it can't be hooked. Carelessly placed common memory hooks may be executed by the wrong address space, in which case they are removed, but no debugging session is created. Deferred hooks are not supported when targeting other address spaces. They can be set only for programs to be loaded into the current address space. Finally, here are a few links to remember. ColeSoft.com is where you can go to get general information about both cXDC and cXDC, and to find out what our friends think about our products. You can also download products and start trials. You can also download maintenance and temporary licensing keys. And you can reach out to our sales team. XDC.com is the front door for a forum we have on LinkedIn where you can ask questions, get tips, and learn about the latest news and maintenance. If you join this forum, you will receive push notifications about maintenance and new developments. We have a number of training videos on YouTube for both cXDC and cXDC. And we keep a Facebook presence for less businessy information about ColeSoft and its people. When you need technical support, you can reach us both by the forum and by email and by phone. You will find our people to be both quick and knowledgeable and accommodating. Thank you.